Why are the definitions of the trig inverse functions what they are? Why do they have these constraints? Well, let's look at this. Let's talk about sine inverse first, which means first we're going to talk about sine of x. Now, sine of x, it starts at 0 and it goes this way like that forever and ever, and it goes this way to the left forever and ever. Now, if we wanted to draw their inverse function, now what I have in front of us, sine x, it is a function because it always passes their vertical line test. Any vertical line I draw only hits the graph in one place. It never hits the graph in more than one place. So now, if I just drew the inverse, y is equal to sine inverse of x. Now, we need to talk about this notation. I do not make up these notations. For sine of x squared is denoted by sine squared x. In fact, sine x to the mth power is denoted this way. For what if n is negative 1? What if m is negative 1? What if you want the reciprocal of sine x? Well, what do? You put a negative 1 here. And I would not say you're wrong, but I would say, you know what? It looks an awful lot like that. I wouldn't shorthand for this. There's not much shorthand. Basically, the shorthand for this is this. Not much of her body, but I would never ever write the shorthand of this way. And I don't want you to think that big S is different than little s. I wouldn't write it that way because it looks just like this. Okay, so that's, I guess one would call that a word of caution. Also, when you see sine inverse of x, do not think, oh, I know what that means. It means that. We're going to assume no. We are going to assume no. Okay? You can argue with me and, I guess I give in to you, but the bottom line is this symbol also means the arc sine. It means the inverse of sine x. This does not. This means the reciprocal of sine x. We can't use the same notation to mean two different things. So whenever the power is negative 1, it's inverse. That is, same for cosine. If you have a negative 1 there, it means the inverse. We have, negative 11 there, well, that means 1 over cosine to the 11th power. The reciprocal of cosine is secant, so it means that. All right, enough of that talk. But it was needed. Now, let us draw the inverse curve. Okay, let's see what's going on, x and y. So, for example, this graph has the point 0, 0. And when you switch x and y, you get 0, 0. This is 2 pi, so that's pi, and that's half a pi. So you have a point when x is half a pi, you go up to 1. So half a pi comma 1, well, that becomes 1 comma half a pi. So when x is 1, you have to go up half a pi. I didn't mean to put a dot there. So when x is 1, you go up half for pi. Okay? When x is pi, you go up 0. So when I switch x and y, which inverses do, I get 0 pi. Okay? So when x is 0, I go up to pi. Maybe I'll extend this line a little bit. Okay? I go up to pi. And when x is 1.5 pi's, I'm at negative 1. Negative pi, negative 1. Well, when you switch that, you get negative 1, negative pi. Something's wrong there. When x is pi, right here, x is pi. When x is pi, you go to negative 1. So we're going to get negative 1 pi. When x is negative 1, when x is equal to negative 1, I go up to pi. Okay? So I am right here. Of course, something is bothering me greatly here. 0, 0 is right. Pi over 2, 1 is right. So that becomes 1. Pi over 2, that's right. And when x is, oh, okay, fine. This is working fine. Now, let's pick some points where x is negative. Or let's even go out to 3 pi over 2. If you go out to 3 pi over 2, when x is 3 pi over 2, y is negative 1. And when you switch that, you get negative 1, 3 pi over 2. So when x is negative 1, you go up to 3 pi over 2. And I don't know why I have a point here. For example, that point right there is pi 0, and when I switch them, I get 0 pi, which is right here. Okay. Now, let us draw some negative points where the first coordinate is negative. Well, right here is negative pi, right here is negative pi over 2, and 3 pi over 2. Well, if x is negative pi over 2, the y value is a negative 1. So when I switch that, I get negative 1, negative pi over 2. So when x is negative 1, I go down to negative pi over 2. I go right there. And the next point will be when x is pi, when x is negative pi right here. When x is negative pi right there, negative pi, I go up none. So when I switch that, I get 0, negative pi. Okay? So when x is 0, I am at negative pi right here. And basically, if you did enough of these, what you would see is that you're getting a graph that keeps repeating up forever using that pattern and down forever using this pattern. Okay, now the problem is this is not a function. This is not a function. Okay, now we could restrict the sine inverse function just to be in here. Just to be in here. Because if I go any more, If I go any more, it fails the vertical line test. If I go any more, it fails the vertical line test. So I only go between here and here. Now, we can define sine inverse there, but these angles from here to here, they're in the middle of nowhere. Let's try to center around the origin. Sometimes you can, sometimes you can't. Well, look, right there, it's well defined. That's the function. We want the sine inverse of x to be a function. So let me erase a lot of this down here. So y is equal to sine inverse of x if and only if x is the sine of y and y is in between, well, let's see. Y goes between negative half pi and pi over 2. Negative pi over 2 to pi over 2. This is why sine inverse is defined that way. That way, if you pick an x value between negative 1 and 1, I'll even denote that. Remember, that was negative 1. If I pick an x value, there's only one y value. If I defined it to go above pi over 2, like including this up here, well then for this x value, I am getting back two answers. The number here and the number here. It's not a function. So I just go between here. And in terms of saying that x has to be between negative 1 and 1, that goes without saying. When you take the sign of a number, you only get values between plus and minus 1. That is the definition here of the sine function, including its restrictions. Now, if you have y is equal to the cosine inverse of x, what is going on there? Well, the cosine graph goes like this. X, y. Now, if you think about it, this portion right here, let me just denote that it goes even more. This portion right here, that's the biggest portion you can have of a cosine graph that passes the vertical line test. Okay, it goes from 0 to pi. Now, if you were to graph the sine inverse, well, what points you have? The point up here, well, that's 0, 1. That's 0, 1, which becomes 1, 0. So when x is 1, we don't go up any. This point right here, where that point is x is pi over 2, y is 0. Well, that has to go to 0, pi over 2. So let's say that's pi over 2. So I'm to go up right here. What about this point right here? Why, that point right here is, well, x is pi and y is not 0, but y is negative 1. And when I switch that, I get negative 1 pi. So when x is negative 1, I go up to pi. And it turns out that it looks like that. Okay, anything bigger, it would go like this. Anything bigger, it will go like that. Now, you can keep any portion you like, as long as it's the biggest portion that passes the vertical line test. You can 100% use this piece as, that piece, as the definition of the cosine inverse graph. You can say that it's defined between these two y values. But why would you want to do that? Why not go near the origin? Now, you can, or, above, hopefully half will be above the x-axis and half will be below. But in our case, if you keep this part above the x-axis, you can't go below it because then it immediately fails the vertical line test. Okay, so what we do is we keep this portion where the y's go between 0 and pi. Only here. That's what y goes from. So, like before, let's get rid of everything down here. We didn't need it. We want to make the cosine inverse function, we want to make cosine y equals cosine inverse a function. So, y is equal to cosine inverse of x. I'm going to use the same terminology I used before. If and only if, that is, here is the definition. If and only if x is the cosine of y and y is in between 0 and pi. Okay, it works. It works. Now, we need to talk about the tangent graph. Okay, what about y equaling the tan inverse of x? Well, this here is one period of a tan graph. And this keeps repeating. It keeps repeating. It's going to fail the horizontal line test. That is, the inverse doesn't exist. But we want it to exist. So we are going to keep this portion. Okay, we are going to keep that portion. So this is pi over 2, and this is negative pi over 2. Now you can draw the tan inverse if you like. Actually, let's do it. So this point right there is 0, 0, and when you take their inverse, it's still going to be 0, 0. So when I draw the tan inverse graph, yep, it's going to have 0, 0. Now, when x is a little bit less than pi over 2, you get really large. It's way up here. That means that when I switch it, you get really large when the y value is a little bit less than pi over 2. Okay, so here's pi over 2. Oh, and when you get large, you get positively large. So I'm going to be positive large if I'm a little bit under pi over 2. So when x is very large, I'm going to be a little bit under pi over 2. That is, I'm going to get really, really close to pi over 2. Especially when x is large. Now, let's look at the other end. if I'm a little bit more than negative pi over 2. A little bit more than that. I get negative large. Well, in their inverse, I will be negatively large if the y value is just a little bit more than pi over 2. Okay, so here is negative pi over 2. And, here's a little bit larger, a little bit more. Well, when x is near pi over 2, when y is near pi over 2, the x value, like right here, I'm not near pi over 2. The y value is not pi over 2. It's that number. But when I go out here, the y value here is a little bit more than pi over 2. And x is very negative. So there is your graph. And y is equal to the tan inverse of x if and only if x is the tangent of y and y is in between negative pi over 2 and pi over 2. Should I put equals here? I don't know, but not putting equal is fine because the y value, and you have this asymptote here, the y value will never ever get to negative pi over 2. And up here, the y value will never get to pi over 2. It'll get arbitrarily close. You tell me how close you want to be. You want to be this close, I will give you an n such that anything past that, it will be within this much. You want to give me a smaller neighborhood below pi over 2? No problem. You want it to be just in there? Pi over 2 is at the top. You want it to be just in there? Well, if you're beyond this end, this distance between pi over 2 and the graph will be no more than that length, that distance. There is the graph, and I defined it. And that's what I set out to do. And this completes this video. If you have any questions on these problems or these arguments, let me know. If you want to tell me I'm wrong, go for it. Tell me where I made a mistake. If you want me to prove another theorem or motivate another definition, ask me. That's what this channel is all about. See you next time. Thank you.